Okay, so dear colleagues, my presentation is about astrobiology of Venus, a topic that is rapidly gaining interest among scientists and not only among biologists. Many years ago, in the 18th century, Russian scientist Mikhail Lomonosov discovered the atmosphere of Venus. Actually, this discovery, in fact, initiated a discussion about the possibility of the existence of life on Venus. Then Venus was considered as a planet very similar to the Earth, but with warmer climate. That's why at first scientists assumed a hot, humid climate and even the existence of life at the poles, where temperature could be lower on Venus. Writers also contributed to the issue of Venus habitability with different types of publications and books. Later, in the age of space exploration, when it was found that the surface of Venus is extremely hot and unsuitable for terrestrial life type of living organisms, scientists turned their attention to the dense cloud layer of Venus. Carl Sagan suggested that microorganisms could exist in the clouds. Then various researchers proposed different types of microorganisms that could dominate in the conditions of Venusian clouds. A sharp increase in interest occurred after the publication of Sanjay Limaye, where he linked the presence of so-called unknown absorber in the cloud layer of Venus with possible biological activity. On this slide, you see Venus in natural light and in the UV range. In the latter case, we can see many dark areas, spots, streaks in which absorption occurs, actually. On the right side, you see a chart that shows the absorption spectrum obtained as a result of spectroscopic study of Venus and the absorption spectra of various biomacromolecules and pigments. And these spectra are in a quite good correlation. It's Venus and different types of biomacromolecules known on Earth. So main current challenges in the astrobiology of Venus, which we will discuss further, are following: extreme conditions in Venusian clouds, absence of water on ancient Venus, feasibility of biogeochemical cycles, and detection of phosphine and its sources on Venus. Extreme conditions for living organisms primarily include temperature. It's assumed that the cloud layer where life can be most likely found is quite hot, and therefore we can talk about the possible existence of thermophilic microorganisms there, according to the Earth's classification. The second extreme factor, if not the first actually, is the very low pH at which only a limited number of known terrestrial acidophiles can survive. So the hypothetical organism in the clouds of Venus must be thermoacidophilic organism. The third extreme factor is very low water activity. On this chart, you can see that the calculated water activity in the clouds of Venus is much lower than the lower limit of water activity at which terrestrial organisms can exist. However, it's assumed that microorganisms can survive in aerosols, microniche aerosols, in a water sulfuric acid solution, where the water activity can be different significantly from that in the surrounding environment. The table shows us compounds detected in the clouds of Venus. Among them, we see sulfur, different sulfur compounds, including the allotrope of sulfur, S8, as well as iron compounds. So in order to discuss life in the Venusian clouds in more detail, we use Charles Cockle's concept of habitability. A series of physico-chemical requirements must come together at the spatial scale of an organism to allow that organism to be active in a given environment. Applying this concept, we can define the dominant type of life as thermophilic due to temperature, acidophilic due to low pH, and also lithotrophic based on the chemical composition of the environment. All these gives us the opportunity to identify microbial communities of hot hydrothermal springs as a metabolic analog of hypothetical microorganisms in Venusian clouds. The table shows microorganisms that could possibly survive in the clouds of Venus, terrestrial microorganisms. They have been isolated from various hot and acidic systems, such as sulfaters and fumaroles. They're able to use sulfur and iron compounds for energy. Among them, we see both bacteria and archaea. For example, here you see representatives of bacteria and also and archaea, and also a hot sulfur fumarole located on Java Island in Indonesia, as an example of this ecosystem metabolic as a metabolic analog of the Venusian clouds. Of course, we must also consider the terrestrial clouds on Earth as environmental analog to the Venusian cloud system, but only environmental or structural, because the difference between these two systems is very large. On this slide, possible coupled biogeochemical cycles, including redox reactions with sulfur and iron compounds, are presented. Some terrestrial extremophiles may also participate in these cycles. You see here. The main features of such a microbial system are strong dependence on aerogeochemistry, specific conditions in microenvironments, and polyextremophily. So the possibility for microorganisms to survive at different extreme environmental factors. An important point here is also a possible formation of ammonia as one of the products that can actually compensate to some extent low pH of the environment. This slide shows the localization of a hypothetical microbial community in the clouds of Venus by geochemical cycles, physicochemical parameters of the environment, and the exchange of matter with the surface due to convection flows, volcanism, and so on. This type of aerosol and the microorganisms that live in it is presented on the slide. In such an environment, various substances can be synthesized by microorganisms to withstand extreme environmental conditions. They are, first of all, stress response regulators of various nature, together with DNA and other macromolecules. All these components can be defined as biomarkers that can be detected when searching for biological activity in this system. And the interesting concept of protecting microorganisms from increased radiation, strong radiation, proposed by Schulze Markus, a German scientist. This is a presence in this system of an allotrope of sulfur S8, which partially absorbs these radiation and in principle can protect to some extent the microbial system. An important point actually is a fundamental difference between the microbial systems in the clouds of Venus and Earth. Terrestrial clouds are a system of not very high density. It can be stabilized only for, can be stabilized only for a short time and are not closed for biological objects. Actually, microorganisms can both be transported from clouds to the surface and from the surface to the clouds. The cloud layer of Venus is a very dense extended system. A hypothetical microbial community in such a system would be completely closed. So extreme heat below surface is very hot, simply unsuitable for any microorganisms of terrestrial type. Extreme cold above, and it must exist stably in such conditions. The microbial system, hypothetical microbial system of Venusian clouds. And involvement in geochemical cycles is one of such possibilities. Finally, the discovery of phosphine in the cloud layer of Venus as a biomarker is a very interesting story. This story is actually still going on. From the very beginning, there was a certain skepticism in it, which became either more or less depending on published relevant articles on these topics. So you see here a lot of articles where some scientists state the presence of phosphine in the atmosphere. Other ones try to say that the calculations were wrong. So it's unclear till now, but this is a story, of course, interesting story, because phosphine is considered to be a biomarker. On this slide, you can see how much the maximum concentration of phosphine in the cloud layer of Venus coincides with the physicochemical conditions that are quite favorable for the development of an extremely acidophilic microbial community. You see here, yeah, the calculated environmental parameters are actually, can give us a chance to say that in this system, kind of extremely acidophilic microbial community can develop. But actually, logic behind this concept, behind the concept that phosphine can be an important biomarker, is that phosphine is produced biogenically in terrestrial anaerobic ecosystems. It accumulates in the absence of oxygen, and its production becomes more beneficial at low pH, and therefore it can be considered as a biomarker. The terrestrial ecosystems in which phosphine was detected are wetlands, sediments of lakes and rivers, landfills, some other anaerobic biosystems. However, it's important that neither microorganisms producing phosphine nor the metabolic pathway of its formation are known yet. That's an important point for microbiologists. The thermodynamic calculations have shown that phosphine can be formed in 2 stages, which should occur under completely, but not completely, but quite different conditions, actually. The first stage, the formation of phosphine, requires low temperature and slightly acidic pH. And the second stage requires high temperature and strongly acidic pH. Therefore, from the point of view of microbiologists, since there is no direct evidence that phosphine is formed by microorganisms in terrestrial ecosystems, it can only be conditionally considered as a biomarker. So this is a kind of the point, argued point for microbiologists and for people who are not directly involved in studying different biological processes. So we know that many scientists consider phosphine as a biomarker. Yes, yeah, it's true. So we can actually observe phosphine in different types of anaerobic systems together with other gases like methane and CO2, which are products of anaerobic degradation of organic matter. But we don't know how phosphine is produced. So we can't say that this is a guess of really biological origin. But this is another story, of course. If we consider the concept of the possible existence of a microbial community in the clouds of Venus, then we should also try to answer the question, how could this community appear there? There are 3 hypotheses for the origin of life on Venus. On its ancient surface, this is the first hypothesis. In the clouds themselves, this is the second concept, and as a result of panspermia. There is a hypothesis of water presence on the surface of ancient Venus for quite a long time. And there were water reservoirs where life could originate. Life could, for example, in this case, originate according to the inversion hypothesis, since even if temperature on the surface of Venus was higher than that on the surface of ancient Earth, then it could be quite suitable for feasibility of all the processes of self-assembly of different complex molecules. So this is the concept, the theory, which is similar to that for biochemical concept of emergence of origin on Earth. There is actually an alternative theory according to which Venus had never water on its surface. Never. So in this case, we can say about the second concept of origin of life in the clouds. All major biogenic elements actually have been found in the clouds of Venus. The system was exposed to solar energy and was under suitable temperature conditions, as well as there were strong fluctuations in concentrations of matter due to the movement of clouds. It can be assumed that under such conditions, complex organic molecules can be synthesized and can be further increase their complexity in microsites. For example, in the nodes of foam structures that can potentially be created in the aquatic environment in the clouds. So this is the concept of origin of life on Venus in the clouds. Finally, life could have been brought into the clouds of Venus in the process of panspermia, either ballistic, for example, from Earth or from other planets of the solar system, or lithopanspermia, it's interstellar traveling of material, or technogenic. But of course, in this case, we can say about this concept only conditionally. It's most unlikely because the time for space exploration is not enough to probably not enough for such hypothesis. But anyway. So this diagram summarizes all the concepts of the origin of life on Venus and shows the succession of an initially acid-tolerant microbial community into a xerotolerant and extremely acidophilic community. So the evolution probably could result in the existence of really xerotolerant, extremely acidophilic microorganisms, which can be still observed now in the clouds of Venus. But before probably conditions on Venus on surface, or at least in its clouds, were much more suitable for life of terrestrial types. So what fundamentals and implications from astrobiology of Venus can be taken into account for further studies? First of all, we can say about cumulative modern concept of the environment. This is actually new type of the ecosystem where aerochemical life mode is dominating. So it's from the theoretical point of view, this is this is unique ecosystem to study. extreme survival capacities of hypothetical microorganisms in Venusian clouds. So we can say about terrestrial extremophiles in hot spring, for example, as metabolic analogs to a hypothetical microbial community in Venusian clouds. Of course, Earth cloud microorganisms also can be considered for further study as an environmental analog, how they can exist there, how they are interacting, how can survive, and so on. New properties of hypothetical Venusian living forms unknown for terrestrial organisms. That could be true because in such ecosystem we can consider a few extreme parameters, which probably we don't know any other ecosystem on Earth that can probably has such a combination of different extreme factors. So as I said before, such kind of microorganisms in Venusian clouds probably can be polyextremophiles, and of course should have specific mechanisms to protect themselves against different extreme factors of the environment. Extended concept of the habitable zone. So Venus clouds and actually endohydrospheres of Jupiter satellites they can be considered as inner habitable ecosystems. So we can say that we can now say about the extended area of habitability, not only connected to solar energy, not only calculated from the distance of the central star, but probably we can apply some other points in order to define such kind of habitable zones in solar system and behind. Space missions to Venus are now planned by several countries, and some of these missions include balloons in the cloud layer and landing probes. And of course, such missions can bring new data that will significantly correct our concepts and theories about life on Venus. And with this futuristic picture about the exploration of Venus, I would like to finish my presentation. Thank you very much.
Thank you very much, Oleg.